Ahoy hoy, Psauce, Nick here, and high five! Why is it called a high five? Well, clearly it's because it's done high and there are 5 digits on your hand. Which is pretty convenient that on both hands there are a total of 10 digits, a nice round number. That's pretty lucky for us. Or is it? Speaking of fingers, sexagesimal is a base 60 numbering system that was used by the Sumerians and Babylonians. This means that instead of our 10 digits, they would have 60 or 59 digits. And when it comes to the 59 digits, the reason why was because they didn't have a digit for 0, meaning that 1 and 60 would be represented exactly the same. However, the numbering system used by the Babylonians wasn't pure base 60, it actually had a sub-base of 10, meaning that the symbols used for 1 to 9 were also included in the digits for 11 to 19, as well as the digits 21 to 29, etc. So it seems that humans have a tendency to use base 10, even when using other base numbering systems like base 60. And the reason why probably has something to do with digits. The word digit actually came from the Latin word digitus, which means finger or toe. And because people would often count on their fingers, it made sense to use the word digit in a numerical sense. And having a number of digits in your numbering system that is equal to the amount of digits that most people have on their hands is pretty convenient, seeing as any digit can be represented by holding up that amount of digits. Another cool thing is that no matter what base you're using for your numbering system, whether it be 2, 16, 8, 10, 10 times 10 will always equal 100. Take for example 10 in binary, which is 2. 2 times 2 equals 4, which is 100 in binary. We can do the same for base 8. 10 in base 8 is 8. 8 times 8 equals 64, which is 100 in base 8. A rather interesting numbering system is Roman numerals, and that 1 is I, 2 is I, 3 is I, and you would think that 4 would be I, and sometimes is, but it's actually IV. And the reason why this is, V is 5, IV just means 1 less than 5, much like IX means 1 less than 10. This helps when it comes to larger numbers because normally 49 would be XXXXVIII, but instead is XLIX. But despite having different conventions, Roman numerals can still be considered base 10, as a number in Roman numerals can still be broken down into ones, tens, hundreds, and thousands. Now you could break down a Roman numeral into sections of ones, fives, tens, 50s, 100s, and 500s. But those numbers aren't all a power of the same number, whereas 1, 10, 100, and 1000 are all powers of 10. So Roman numerals could be considered base 10, but can also be considered to have a sub-base of 5. Polydactyly is when someone is born with extra digits. This could be on their hands or their feet. Now, if most humans had 6 digits on each hand, we would most likely be using a base 12 numbering system. An advantage to using base 12 over base 10 is that 12 has 6 factors, where 10 only has 4. The factors of 12 being 1, 2, 3, 4, 6, and 12. Now in base 10, when you divide 1 by 3, you get 0.33333333 recurring. However, in base 12, you get 0.4. Now on the flip side, if you were to divide 1 by 5 in base 12, you would get a recurring number, whereas you get 0.2 in base 10. Now recurring numbers do pose a problem for conversion between bases. If you take, for example, 0.3 plus 0.04 and enter that into Python, you would get something along the lines of 0.3399999997. This is because in binary, both 0.3 and 0.04 are recurring numbers. Now a computer can handle this to an extent, which is why you will get the correct answer of 0.7 if you add 0.3 and 0.4. But if you want precise results in your calculations, you might want to go for a different format. So instead of going for binary format, maybe a decimal format. Now computers can store decimal information, but this is not as optimal as storing it in binary, because every digit needs to have 4 bits. And unless you have hardware that's specifically designed for decimal calculations, then calculations are going to take a lot more processing power. But all that ignores a problem. Base 10 still has recurring numbers. If someone were to divide 1 by 3, for example, you'd get 0.333333333 recurring. Now, a more precise way of storing information might be to store things as fractions. So rather than storing something as 0.3333333, you could store it as 1/3. But there are still issues with fractions, like irrational numbers. But it seems that no matter how many digits you use or no matter how you store information, there is no way to truly be precise. And it seems that the universe has never been precise. DNA, for example, does not replicate itself precisely. There are errors every so often, mutations. And all these imprecise replications allowed for humans to be here today to just wonder and ask questions like, why is a high five called a high five? And as always, thanks for watching.